Hey friends, do you remember how we spent all that time learning about valence electron configurations and talking about how many valence electrons an atom has? Well, now we're going to see why it was so important to learn that. Now it will all begin to make sense. I promise. Let's review by taking a look at the periodic table and talking about how many valence electrons each group has. Group 1, alkali metals with a valence electron configuration of Ns1 have one valence electron. Alkaline earth metals, we're also going to skip over transition metals because the amount of valence electrons that they actually use varies. And we're going to end up at group 13. These atoms have a valence electron configuration of Ns2np1, or have 3 valence electrons. The carbon family has 4 valence electrons. The nitrogens have 5, the chalcogens have 6, the halogens have 7, and finally our noble gases have 8. Why does this matter? Well, remember, the goal of every atom is to fill its outermost end shell. Atoms achieve this by getting an electron configuration of Ns2np6 on their outermost end shell for a total of 8 valence electrons. How do they get there? By sharing electrons through covalent bonds. Through the 2 covalents shared in a covalent bond, the atom now has access to 2 electrons instead of 1. So why do we care? Well, because the number of valence electrons an atom has determines how many electrons it needs to acquire through bonds to get that coveted status of having 8 valence electrons. Therefore, the number of valence electrons determines the number of bonds that an atom can make. What do I mean? Well, let's look through element by element, starting with hydrogen. Hydrogen is in group 1, although it is not an alkali metal. It has 1 valence electron, and we can represent it with a dot structure like this, where each dot represents a single electron. Now, hydrogen is an exception to wanting 8 electrons. It only has n equals 1, or 1s, a 1s orbital. So it is aiming for a duet, or 2 electrons, rather than 8. So hydrogen is going to make 1 covalent bond to have a total of 2 electrons. Now we're talking about covalent bonds here, so we skip over group 2. We skip over transition metals because they have their own rules, and we end up at group 4. Carbon in group 4 has 4 valence electrons, and we draw carbon's dot structure like this. Carbon has 4 valence electrons, so it needs 4 more electrons to get 8. So carbon will make 4 covalent bonds. Let's hop over to nitrogen next, which has 5 valence electrons. We draw the electron dot structure like this. And whoa, we have something we haven't seen yet. 2 electrons that are paired together. These electrons are what we call a lone pair, which means they are a pair of electrons that do not participate in bonding or are non-bonding electrons. So if we have 2 non-bonding electrons in a lone pair, we have 3 single electrons that will want to form bonds to give us a total of 8 electrons. So nitrogen will make 3 bonds. Next, we have oxygen in group 16, which has 6 electrons. When we draw out the electron dot structure, we see that oxygen has 6 electrons with 2 lone pairs. The 2 electrons not in lone pairs will want to form bonds to get a total of 8 electrons. So oxygen and other elements in that family will form 2 bonds to get 8 valence electrons. Now we hop over to fluorine in our halogen family, or group 17. When we draw, fluorine has 7 valence electrons, and when we draw out the electron dot structure of fluorine, we see that fluorine has 3 lone pairs and has 1 lone electron that is ready to bond. So fluorine will make 1 bond to reach 8 electrons. Finally, we end up on group 18, or our noble gases with neon. If we draw, neon has 8 valence electrons. So if we draw out neon's Lewis dot structure, or electron dot structure, what we see is that neon has a total of 4 lone pairs with no electrons that are wanting to bond. So since neon already has 8 electrons, it doesn't want to make any bonds, and it won't. This is why the noble gases rarely form bonds with the other elements, because they already have a full outermost electron shell.